Good afternoon and welcome to the Aula of Maastricht University. My name is Teun Dekker and today I will be representing our Rector Magnificus, under whose authority, hopefully, the doctorate will be conferred in, slightly over an hour's time. We really appreciate that so many of you have come to Maastricht to be part of this, ultimately this ceremony, but also celebration of Lex's work. We know that we are a little bit of a corner of the Netherlands, and that's why we really appreciate it when so many people come over and to add their presence to this special occasion. We hope that this will be, a festive thing, an opportunity to share the work that has been done and also to celebrate the achievements of, what has been no doubt a long process. What will happen is I will open the ceremony in a moment, then there'll be an initial presentation, and then we'll have about 45 minutes of, opposition and hopefully stirring rebuttals to that opposition, and then we will retire to confer and decide whether or not we feel that the defense was worthy of the doctorate, and then we'll come back for the actual conferring of that doctorate before we head off for a reception. So it should be, hopefully interesting. I should ask you please to turn off your mobile phones, because nothing is more annoying than when you're in the flow of things and you really are swinging in your answer that the mobile phone goes off. So please make sure that all devices are switched off and enjoy the show. Hereby I open this academic ceremony in which Lex Greeven will defend the academic thesis Decoding Beauty, Rare Baryonic Decays and SciFi Detector Commissioning. May I invite you to present a summary of your study and the conclusions of your thesis.
Yes, thank you. Dear Pro-Rector, members of the degree committee, dear friends and family, it's great to see so many of you here to be present on this special day. I will give a presentation now to explain my research. It will be in English, but the presentation also has Dutch text on it, so hopefully everybody can follow it. And the goal of my presentation is to explain to you the title of my thesis. So, Decoding Beauty, Rare Baryonic Decays, and SciFi Detector Commissioning. So I hope by the end of these roughly 15 minutes you will kind of understand what is going on here. So, I did my PhD in the field of particle physics. So I started with a first brief introduction on what actually is particle physics. It's basically the science of studying what everything around us is made of. And it goes to the smallest possible scales. So I put here a certain amount of centimeters. I think there's like 16 zeros or something there. So you get a bit of a scale of how small these things are. And if we see here on the right, we have a little droplet of water. And water consists of molecules. And these molecules, again, consist of atoms and electrons. And if you zoom in even further, this atom then consists of a nucleus, which has a proton and a neutron inside. And those, again, also even exist of smaller particles, which we call quarks. And on this quark level is kind of what we are dealing with. So it's very, very tiny things, and also for us at very high energies. But in the end, we consist of these kind of particles. Now, there is a certain thing called the standard model of particle physics. I know some people try to avoid putting this in their presentation, but I think it has a good place in it. And this is basically the theoretical framework to describe particle physics. And what it does is describes matter and interactions between matter, so how matter can interact with each other. And you can see a picture of it on the right, where in the purple we have the quarks, which I just told you about. So for example, protons and neutrons are made of it. And they come in 3 generations. And there's also leptons, which includes the electron, which you can also know in the form as electricity, for example. There's also the particles in red, which are the force carriers. So these describe the interactions between the particles, which I'll come back a bit to later as well. And there's the Higgs particle. And maybe if you spot something here already, you see a particle called the bottom quark on the third on the middle. And an alternative name for this is beauty quark. So this is already the first word of my title that you can learn now. So that's where beauty comes from. And this is a very well-tested theory experimentally. So many years of research have gone into this, and people investigated it, and it seems to work things very well. And like a bit, you can see it's like the Lego of the universe. So all these things are like individual Lego blocks you can put together to form particles, which is what I show a bit here. And you can see in yellow we have the standard model Lego blocks. But there's a thing about the standard model. It's incomplete, so it's not describing everything we know of. For example, as you can see here, there's a little brown block that says dark matter. And dark matter is something we observe in the universe, but the standard model does not have an explanation for it. So it's something that has to be added, so we have to add a little block to it. Also, gravity, for example, is also not described by the standard model. And maybe, therefore, we can use these red blocks, what we call new physics, so something that's not inside the standard model, to extend it and further describe how things interact with each other. Okay. Now, the beauty quark, I already mentioned it briefly. It's my favorite particle, otherwise I wouldn't be here probably. It's the third generation, so it's quite a heavy particle. I highlighted it here. And one thing it can do is it can form particles called baryons together with two other quarks. So there's three particles in general, three quark particle. And this is the second word of my title that you learn, a baryon. So a baryon is a particle that consists of three quarks. And in my case, it's a beauty baryon, so a baryon with a bottom quark inside. And these baryons can decay in interesting ways. And you probably all heard of decay, certain like nuclear power plants, they work with decays of uranium. But in this case, we work with the decay of a baryon instead. And some of these decays are very interesting to us because they are very rare, so they don't happen very often. And with this, we can measure these properties of the standard model and maybe test for possible new Lego blocks for the standard model. Okay, so I mentioned that they're rare, but maybe I give you a moment to think about what actually is a rare decay. So if a particle decays once every 10 times towards present decay, or maybe one every 1,000, 10,000, 100,000. Well, what we claim is rare is about 1 in every million or 1 every 10 million. So if I have 10 million particles, only one of them will decay in the specific way that we're interested in. So it's quite, you can imagine it's quite a challenge to measure these things because they happen very rarely. Okay, so as I said, some of these B decays are very rare in the standard model, so 1 every million or 10 million. It's a bit like looking for a needle in 10 haystacks. So here you can see me looking through a haystack for the needle. And you see it's all the little B quarks, and then I find one specific one, which is a B and an S and two L's, which I'll come back to later what it means. And this is my supervisor, Niels, who's sitting right there saying, congratulations, you found it. But it's a big searching through these things. But an interesting thing could be that if there is some new physics, which enhances the amount of these decays, so if there happen more of them, then maybe you find more needles in your haystack than you expect. So maybe I would expect to find one, which I found here, but maybe there's 10 or so. And this could be an indication that something is going on. So we need to study these rare decays to search through the haystacks. Okay, I briefly mentioned it, but the specific decays we're interested in are these B to SLL decays, which is a beauty quark going to a strange quark and two leptons, so it could be an electron or a muon. And they can happen in different ways. So in the standard model, they can happen through what we call a penguin or a box diagram. And potentially, there could be new physics, which happens in a tree diagram. But to make it a bit more clear, maybe, or maybe even more confusing, is there's these diagrams that describe it. And these are the actual diagrams. So on the left, we call this a penguin. If you want to know why it's called a penguin, you can ask me at the reception later, because there's a story behind it. And on the right side, it's a box. So you can see where the name of the box comes from, because you can draw a little square inside here. But maybe it looks a bit overwhelming, but what I want you to take away from this is that in the standard model way, so on the left and then on the right, you need to have this loop inside. So there have to be many particles interacting with each other to get to to what we want. So in this case, a beauty going to a strange and two muons. However, if there's new physics, which is on the bottom, the diagram, we have here a particle that can couple directly to these two particles and create, basically you only need this one single particle to do it. So this is not so suppressed, so to say, and therefore this maybe can happen more often again. So this is kind of what we're looking for. So because it's rare in the standard model, maybe this new physics could have an effect we can actually measure. Okay, now I explained with what we did, but then the question is where do we do it? Maybe you've heard about it, but in Switzerland, there's a very big ring underground called the Large Hadron Collider. It's based at CERN, which is a research complex in the France-Switzerland area. And it's the largest particle accelerator in the world. It's, I think, 27 kilometers in circumference. And it also has the highest energy. And what we do here is we shoot protons on each other. So protons I mentioned earlier, they are also in atoms. And if you shoot them together, they kind of explode into many other particles that you can then measure. And there's 4 major experiments, which are also indicated on this graph here. But of course, the best one is LHCb, because that's what I did my PhD on. And then if we think about, first a little picture of how this is then look like. So this is a picture from inside the tunnel underground. And what you can see here, this blue thing is where the beam goes through. So there's a lot of magnets you need to keep it in place, but it's a very impressive piece of engineering, I would say. Okay, then a bit about the LHCb experiment, which is an experiment I did my PhD with. And it's an experiment focused on the beauty quark. It's already in the name, because it just stands for Large Hadron Collider Beauty Experiment, for the beauty quark. And basically the way you can think about it is like a super fast photo camera. So these collisions are happening millions of times per second, and we want to be able to take a picture millions of times per second, but then a picture of these particles. So it's a bit more complicated than just your normal photo camera. And also one thing I want you to take away from this is that it consists of many layers of subdetectors. So there's not this, it's not just one tiny thing, it's actually quite large. There's also a scale here, about 20 by 5 meters or so in total. And then what we do is we measure the data with it, and then we try to analyze it. Here's a picture of me in front of the detector, and this gives you a bit of an overview of the scale in real life. So I'm here in the front, and the whole experiment is surrounding me, and it's even a bit cut off. The whole thing doesn't fit on the picture. So it's quite large, I would say. And a picture, this is kind of one of these pictures that shows up then in the photo camera, so to say. So this is one collision that is measured. And what we get out are these tracks of particles. These are the lines you see going from left to right through the screen. So these are particles that are reconstructed. And then these blobs, what are on the right, is energy measurements that are being done as well. So it's kind of like a big picture. And then we collect millions and millions of these to analyze the data. Okay, now I'm going to go a bit more in detail because I also want to show what I did myself. So I worked on these rare baryonic decays, like I explained before. And we measure in specifically this lambda b to j psi lambda. So lambda b is a baryon going to a particle and another lambda. And we also measure the lambda b to lambda lepton, dilepton pair decays. And the one in green is what we call the control channel. So this we use to mostly verify our measurements and see we're doing everything correctly. And then the one in blue is our signal channel. And in this case, these leptons here, this dilepton pair, can be an electron or a muon. And the muon is a little bit the heavier brother, so to say, of the electron. So it's a very similar particle. And what we can do is then we can measure something called lepton flavor universality, also abbreviated LFU. And we call this ratio R lambda. And this is shown here on the right. So basically what the standard model predicts is that this decay happens equally often for a muon pair or for an electron pair. So you can measure this ratio, and if this ratio is 1, that means it agrees with the standard model. However, if there is this new physics, like these new building blocks of the Lego that I was talking about before, maybe this ratio is not 1. And therefore, we can measure this quantity and then see if it's 1 or not, and then see is there new physics or not. So this is what I did for my thesis. And then the results I show here. So we successfully measured the lambda b to j psi branching fraction, and branching fraction means how often does this decay happen. So for this one, it's less than 1%, so 0.3, not even less. Yeah, it's a very small amount, but still for us relatively large, because the rare decays we consider are 1 in every 10 million or so. And the picture here on the right, you see this kind of straight line slowly exponentially going down, and then the big peak on top. And this big peak is actually the decays that we're interested in. So these we measured. So you can see, you actually do see something. It's not a bit of an abstract. And then for the lepton flavor universality measurement, we use this result as an input for the measurement. And also there, we've been taking big steps towards measuring R lambda. We've been first measuring these control ratios. So basically, it's similar ratios that about electrons over muons, for example, but then for the control channel. So also for this j psi lambda decay. And these are shown on the bottom right here. So these should be in agreement with 1, but there seem to be a bit below it. But this is something we were still working on in the analysis. And also after I finished my PhD, people are working on it. And also what we did is we first looked at the rare decay mode. So we were looking actually at, can we see if anything is there or not. Okay. Then also my research had a second part, which was the SciFi detector commissioning, which is also the second part of my thesis title. And this comes back to the fact that the experiment was upgraded around 2018 to 2022, plus minus. And a big part of the detector was replaced. So multiple of these sub-detectors that I mentioned before, multiple of the layers of the detector, they were replaced to be able to deal with higher collision rates, so taking basically more pictures than before. And this needed a complete new set of hardware and electronics. And these have to be commissioned, so to say. And I worked on multiple parts for this. One part was the decoding of the data. So we get a big data stream out, which consists of just raw zeros and ones, like bits. And those have to be converted into something we can actually use inside the software. So this is part of what I did. And another big part was all these electronics inside the detector. They have internal clocks, and these have to be aligned with each other. Otherwise, you get weird effects. So what we do is called a timing scan, where you scan these clocks for different time values and then iterate over it to see if it works. And here's a picture on the right. You see these black mats in the background. That is the SciFi detector. Actually, this picture is taken from inside the big magnet that's in the detector as well. And you can see also here, maybe it's nice to see, in the middle you see the beam pipe going. So this is what's held in place by these cables. This is actually where the particles fly through to collide. Okay, so then a little bit more detail about these timing scans. So basically every SciFi channel, so every individual channel, has 4 clocks inside, 4 clocks for readout, and we have to find scans for these and find the optimal setting. So we have to see what is the best value of this clock. And I show a picture here on the right of how it happens. Basically what you have to know is that 0 is good. So if it's 0, there's no errors, and we have a stable connection. So what we then do is we find this region where it's 0, and then go sit in the middle, say, okay, this is a stable position. And this plot on the top then comes back into the plots on the graph on the bottom here, where it is one tiny green line. So every individual of these green lines comes from these plots on the top. So it's a lot of information condensed in one picture. And then what you can then see in the center, there's a green line which forms a stable setting. And these we then can use, find the common setting for the whole detector and then use this for operation. Actually, we did manage to find successfully optimal settings for all these clocks. And now these have been applied to the detector, and the detector is fully operational, at least when I finish my PhD. I hope it still is. And we've been collecting new data for future analyses for these rare B decays that I was mentioning. Okay, so in conclusion, I think rare beauty decays are very cool. I spent 4 years working on it, and we did some cool things. We successfully measured these lambda B to J psi lambda control modes, and we took important steps towards measuring the lepton flavor universality R lambda ratio. And also the SciFi detector has been commissioned, at least mostly, and we found best clock settings for these values. And yeah, I think there's exciting times ahead for LHCb in the new upgrade. And here's a picture of me at the beginning of the PhD. So you can compare me to how I look now and see if I aged a lot or not. Thank you very much. Thank you for your attention. And I'll give back the word to the pro-rector.
Dear candidate, thank you for that fascinating presentation. Everything seems to be in the title, and the rest is details.
Exactly.
To discuss those details, the opposition will now be opened by Professor Gerco Onderwater from Maastricht University.
Dank u wel, meneer de rector. Meneer de promovendus, dear candidate, it's my privilege to be the very first one here to congratulate you on this very well-written thesis that I had the privilege of reading already months ago to allow this defense to happen. I see that the quality of your writing has also translated into a very nice assignment to an AI system to create your cover, which I also find of a particularly high aesthetic value. So congratulations on both the content as well as the cover of your thesis. It was a pleasure to see and read. Now that said, we have to have a good discussion here, and since I'm the first one, I think I will simply start with the very beginning, and that is actually your proposition number 1. So perhaps you can ask one of your paranyms to read out proposition number 1.
Sorry, I'm a bit short. The study of beauty baryon decays provides complementary information to the more commonly studied beauty meson decays and is essential for a complete understanding of the standard model of particle physics.
Okay, thank you. Intriguing proposition, as they should be. And whereas I completely agree with the part before the comma, I think I totally disagree with the part after the comma, but that could be my misunderstanding, and I will explain you why I disagree. And that is that word essential there. I looked it up in the dictionary. What does essential mean? It means being of essence, which is sort of a circular definition, but it also means necessary, and in the end it all boils down to you cannot do it without. Now, I'm very sorry, I don't believe that for 1 second, but perhaps you can explain and convince me in the next few minutes why it is really essential that we do this.
Dear highly esteemed opponent, thank you for your kind words and your question. So, if I understand it correctly, you want to know why we measure these baryons also next to the mesonic modes, is that right? Or why they are essential?
Particularly why they are essential.
Okay.
Yes.
I mean, so, baryons consist of 3 quarks instead of 2 quarks, and often the third quark is called the spectator quark, because in these, sometimes in these decays it doesn't interact. But yeah, I think if you only measure the mesonic modes, you kind of disregard a large part of the standard model. And there's also things that make baryonic decays different from mesonic decays. For example, the form factor that describes the interaction between the quarks during the decay, these are different from compared to the mesonic modes. So this is already something else you probe with them, which you cannot measure with the mesonic modes. Also, another aspect you can consider is that at least the lambda B baryon has a spin half and not a spin 0 or spin 1. So it's not a full integer spin, but it's a half integer spin. And this can also lead to different effects in the interactions and in the decays. So I do think they provide information that is, maybe essential is a very strong word, but the proposition has to be a bit controversial maybe. But I do think that it is an essential input for the standard model, because if you wouldn't measure them, you wouldn't know anything about it. So I do think it provides information.
Now I'm willing to go along with you a little bit there, but I'm not completely convinced yet. Because what you're saying, this complementarity or the things that you would not know, at some point that would show up in, say, a global fit. And now I have to quickly look where the picture is of that global fit. Let me see, somewhere around page
11.
11, yeah, oh, thank you. Yeah, you know your thesis very well, yeah. Compliments again. There, your essential decay channel, I don't see it.
No, that's right.
So, yeah, so why is that?
That's because it hasn't been measured yet, or at least not in the ratios we do. There have been measurements on these rare lambda B decays, especially the muonic modes, because they are easier to measure due to the muon interacting less. And this is part of the reason why we do these studies, for example, the R lambda, to provide an input to this global fit. And indeed, I do agree with you that these C9 and C10 parameters are also coming back in the mesonic decays. But it could, for example, be that there is some kind of new physics that couples maybe only 2 spin 1/2 particles or so, or only interacts better in these kind of baryonic decays than in the mesonic decays. And then this could show up maybe in your diagram. And maybe it's also because the form factors are independent. Also, it's like an extra independent cross-check on these results, because maybe there's some systematic error in these analyses, for example, or there is maybe new physics doesn't show up in mesonic modes, but it does show up in baryonic modes. And so you could, for example, envision doing measuring all these modes that are here for the mesonic, but then also with baryon counterparts, and then do a baryonic global fit. And maybe this agrees with the mesonic one, or maybe it disagrees.
It's of course still somewhat speculative, but I'm willing to accept that. Do you perhaps then have a feel, or maybe not, I don't know, what a blob in this plot would then typically look like? Because most of these seem to be, well, okay, let's say a banana on its side, and they're all fairly parallel. Would a lambda decay be orthogonal potentially?
It's a good question. I would expect them to be similar shaped to the Masonic ones. I don't have a good reason for it, but my gut feeling is saying it should be a similar shape. But I would expect them at least to be even maybe a bit more banana shaped, because part of the problem with these baryonic decays is that we measure fewer of them, or they're harder to produce, for example, and harder to reconstruct. So the uncertainty will be quite large. So this is something that you would be able to notice as a difference between the Masonic and the baryonic modes.
Okay. Now, I think more banana as a replacement of the word essential, I'm willing to accept. Thank you for your answer, and give the word back to the detector.
Thank you. The opposition will now be continued by Professor Ulrich Uhr from Heidelberg University.
Yeah, dear candidate, let me first congratulate you for this very nice thesis. I'm also very much impressed by the cover, which I learned only today. I saw it today the first time. Let me jump to the end of your propositions and also to the end of your talk. To proposition 9, maybe somebody can.
All we have to decide is what to do with the time that is given us.
Yes, exactly. And I think you have spent a lot of time, many months, in time calibrating the scintillating fiber tracker. And honestly, it was also only a part of this calibration. So can you tell us which different ways or which different calibrations were necessary, and why it is so important, and why you have invested in a good way your time to calibrate that detector?
Dear highly esteemed opponent, thank you very much for the kind words and your question. So indeed, my part, of course, is only a very small part of the whole commissioning of the SciFi detector, as I'm sure you're aware. And maybe this also comes back to my proposition. All we have to do is decide what the time is given to us, because I only have limited time as well as a PhD student, so you have to choose your battles. But indeed, so the timing scans was one important part of the calibration. But many things have to be checked. There's a lot of cables, for example, coming out of the detector, and they have to be made sure, are all the cables okay? Are they actually transmitting data, for example? Are they mapped correctly to what we think we are? If I have a cable coming out, is it actually connected to where it's supposed to be? So this is a big part that people still have to do. There's also the thresholds that are set for if we record signal or not. These can also be scanned. There's something called a threshold scan. It's a bit of a similar procedure to the timing scans, but for different properties. This was not part of my personal work, but I did see people do it when I was working at the control room at CERN. So there's many things that have to be taken care of. Indeed, as a single person, I think it's not possible to do everything, and I think that's why it's so nice that we work together with so many people in this experiment, and we make things like this possible.
Yeah, but it doesn't become clear why it's so important to correctly time align the detector, and where could possibly things go wrong, and maybe you can stress this?
Yes, sure. So we have to make sure our detector is time aligned completely, because otherwise, say, one of my channels is not adjusted. Either I maybe don't get any data, just get rubbish out because it's off in the clock cycle, or maybe I get the data that comes from the previous collision that's happening because there's so many in a row, and then you're not measuring correctly anymore. And indeed, often what we saw is if these channels are not set with these correct time settings that we found, then they just only transmit errors. We don't get any useful information out of it. So basically, without these proper settings, we cannot operate the detector, and we cannot measure the particles with it. I think this is mostly why it's so important, because otherwise, I think it's only one small step. I think this also shows why it's such a complicated thing, because it's only one part of this whole calibration procedure that's needed. But without it doesn't work.
But you have you use granularity of 50 picoseconds, which is a very short time, And why it's so important to adjust it to 50 picoseconds? Events happen with 25 nanoseconds. Why 50 picoseconds?
It's a good question, but I mean, we scan it with 50 picoseconds, I think, because this is the resolution that's available to us as well. So this is the smallest we can go. But also, if you look at, for example, the plots in chapter 7, if you go to, maybe page 113, where we see this overview of one of the clocks that's measured, in this case, the FPGA main scan, you can see that actually, so in the light green band, it shows the common interval. And actually, this is quite a wide range. So these plots are in DAC values. But if you convert this to picoseconds, this is probably, I think, the width is like 2,000 picoseconds or so. So it's quite a wide range. Then if you have this resolution, why not use it, I would say, and just go find the center, and then you're also more stable. Another thing you can take into account is that maybe over time, your error-free region starts to become smaller due to detector aging effects or so, with the radiation damage. Then I think it's better to be exactly in the middle, where you have the good line, to not accidentally fall out of this and then maybe do get errors.
So in summary, you have well invested your time.
I would say so.
Thank you. Thank you very much.
Maybe a follow-up question?
Yes, maybe a follow-up question concerning your analysis. Actually, I mean, like you said, you were mostly measuring ratios. And it started off by saying, okay, I measure my branching ratio also as a ratio. And also you have showed one of the plots where, you measured something which was not so good, and then you built ratios, and then you said, okay, now it's a little bit better. That sounds a little fishy. So can you explain, first of all, why you measure ratios and not absolute value of the branching fraction, and why you use this trick? It sounds like a trick, yeah? I mean, you have two numbers which don't fit, and then you divide them, and then suddenly it fits.
Yeah.
Why you use this trick in addition?
Yeah, it's a good question for sure. So for the branching fraction, it has two reasons. It's firstly because the absolute production of these lambda B baryons is not known, so you have no absolute count of how many there were produced. So what we do is we then normalize it to a mode that we do know, which in this case was the B0 to J psi k short. And that one is very well measured at the B factories, for example, Bell and Babar. So with this normalization channel, we can calculate, okay, we found so many of these with a known branching fraction, and therefore we can, we indirectly know our own branching fraction for
But let me interrupt you. I mean, you say that the number is not known. I mean, the cross-section is known in principle.
Yeah, but with a large uncertainty, I guess. Yeah.
Yeah, how large, do you know?
By heart, I don't have this number.
Okay,
but it has a large uncertainty. Maybe the second part is that also many systematic uncertainties cancel out in these ratios. For example, there's both muon reconstruction in top and in the bottom, and these then, because they're in the ratio, you divide them out with each other. So your measurement becomes more robust, so to say.
As we have seen.
Yeah, hopefully. Yeah.
Yeah, thank you very much.
Thank you. The opposition will be continued by Professor Paul de Jong from the University of Amsterdam.
Thank you. Dear candidate, let me also congratulate you with the completion of your thesis, which was really truly a pleasure to read. You made a contribution to the study of lepton flavor violation, or at least some hints of lepton flavor violation that had been made in the past. This time with baryons. That's interesting. Probably essential for a complete understanding of the standard model of particle physics. And you also made contributions to a new detector, the SciFi. So let me start with asking you about the SciFi. I'm interested myself. What were the design considerations when you started, and your colleagues started building this detector, other than there's a higher luminosity and our old outdated outer tracker cannot handle it anymore? What other design considerations are there, and why did you end up with a SciFi detector?
Dear highly esteemed opponent, thank you for your kind words and your question. So yeah, indeed, the detector was replaced because people probably did studies and found that the old outer tracker couldn't handle the larger amount of tracks, for example, that are produced because of this higher luminosity. So I think this was probably the main reason why it was upgraded, as you already mentioned in your question. And then why they chose for scintillating fibers, I think partly because it was an interesting technique that wasn't fully applied yet at a CERN experiment.
But that's usually not a good reason by itself.
No, it's true. Yeah. Well, maybe partly for funding, but okay.
Maybe it's more expensive than any other type of detector. So then it's against.
Could be.
Works against you.
Yeah, could be. No, but I think part of the consideration was maybe also in getting an increase in spatial resolution. And with the fibers, they're a lot thinner than and you measure out the photons instead of with the old the drift tubes, I think, where you measure the electrons that come from it, basically the charge. So the fibers are thinner, so I guess it gives you a higher spatial resolution. You can deal better with the higher amount of tracks. I think those were probably the main points.
So, do you know what position resolution the detector was designed for? And has this been achieved in the data taken so far?
I think it is mentioned somewhere in my thesis, if I remember correctly. And I know at least the one for the auto tracker is mentioned. Somewhere in chapter 3. Let me double check. I don't know these numbers by heart, unfortunately. Yeah, so at least on page 20, there's you can also see the picture of the OT, and it says also the position hit resolution of the OT is around 200 micrometers, which then leads to a resolution on the momentum if you combine it with the whole. And also I mentioned it here later. The SciFi tracker uses 250 micrometer size scintillating fibers to measure the particles, but I don't mention specifically the hit resolution on it. Yeah, this is true.
Okay. Was timing resolution also in factor?
Yes, because for the drift time, it takes a bit of time for these hits to be measured, I would say. And maybe with I guess the photons travel quicker. You don't need to wait on this drift time, is my, I would say my informed guess. So you measure the photons in the fiber and they travel with the speed of light. I think this would be my answer.
Yeah, but I understand that you digitize the signal at 40 megahertz, because I was also triggered by this 50 picosecond number that appears in your thesis at some point, but it doesn't seem that you actually make use of that other than adjusting the timing of your detector, but there's no way that you can reach sub-nanosecond accuracy.
To read out more, you mean, or at quicker rates than 40 megahertz? Yeah. Well, I mean, at some point, I guess it is not needed anymore because the collisions happen at a certain frequency. So if we would measure faster, you would just measuring the empty data. You would not be measuring collision. Maybe you would get offset to for example, to the LHC clock, and therefore not know what collision you're measuring anymore.
Okay. Then I would like to still ask you a question on the analysis, if I'm allowed to. On table 5.1. And you talk about page 67, by the way. I think this is the general discussion on the resonant mode and selection efficiencies and what have you. And you gave a lot of numbers in this table 5.1. But I was wondering what stripping actually means, and whether you say stripping and reconstruction together in one number. What do they have to do with one another? And is one 100% efficient and the other not?
This is a good question. So stripping is something we do at LHCb to reduce the size of the data set. So it's basically some loose pre-selection cuts you apply so that you don't get overloaded with large amounts of data.
Is it 100% efficient?
It's not. Well, we don't know. We don't know the split number. We only know the combined number. But probably you lose some kind of events, I would say. Maybe it's probably quite efficient because the cuts are quite loose. But I find it hard to claim 100% efficient.
Okay, and these numbers, have they all been determined from simulations only, or are the numbers which are determined from simulations and some from data? And could you, in principle, determine them all from data?
So the basis comes from simulation, indeed, but we do these data Monte Carlo corrections that I discussed in chapter 4, where some of the efficiencies are calculated from the data. For example, the PID efficiency we calculate on data, and the trigger efficiencies we calculate on the data by using the methods described in there. I would fully measuring on data. I'm not sure if this is possible. I mean, the reconstruction is a bit difficult to measure if you only have data, because you don't know exactly what was your before the reconstruction, because you don't measure it. So I think this would be a difficult part. yeah, maybe you could, maybe some of the pre-selections potentially, but it's hard to verify them. I think we use the data more for things like the PID, which is more of a, it's not a property of the decay, but it's a property of the particle. So the muon, it doesn't matter if the muon, at least it matters less if the muon comes from a lambda beta J psi or from a more often produced B plus to J psi k or so. So for these, you can use the data, and I think it's better to use the data because the data is what you actually measure. But for the other ones, I think simulation, we can trust the simulation enough after applying all the corrections that we can take those efficiency numbers.
Okay, thank you very much.
Thank you. The opposition will now be continued by Dr. Carrie Vos from Maastricht University.
Thank you. So, dear candidate, first of all, let me join my colleagues in congratulating you on finishing this beautiful work, and also on the very impressive measurements of the lambda beta lambda J psi with the factor 3 improvement. That's very nice. I would like to start with asking a little bit about the corrections of the Monte Carlo. Sorry, Sylvia. Stelling number 3.
The measurement of the lambda B to lambda dilepton decays is not possible without correcting the available simulation to match the data, which is a complicated and error-prone process.
So first of all, I think the part behind the comma I agree with. As you nicely describe in your thesis, this is a lot of work indeed. But about the first part, I mean, so if you match your data to simulation, what happens if you have new physics?
What happens if you have new... Oh.
Yeah.
Dear esteemed component, thank you very much for your question and your kind words. So your question is, what happens to new physics if I just match it? Well, say you would measure something in your data that's different from your simulation, and you don't correct the simulation. You don't know if this comes from the fact that your simulation is wrong or that maybe there's new physics.
But for example, I mean, if I look at this, you also look, for example, you correct for the lambda beta J psi lambda angular distribution, which is also measured.
Right.
But if there would be new physics, maybe also those distributions would be different from what you're expecting, no?
This is true. Yes, for example, also the Q-squared distribution could be different. But one of the things you could do, in principle, what has been done by the Masonic counterparts of the analyses, is measure these ratios in bins of Q-squared, for example. So then you could see if there's a dependence in Q-squared, or you could, in principle, do the same for the angular parameters. Those are also separate measurements for the, also for the baryonic modes, but mostly for the Masonic modes to measure these angular parameters in bins also. But yeah, I think for the specific decay study here, the amount of data that's available is just not enough to do this. So at the moment, we were aiming to measure it in the low and the high Q-squared region. But the question is if there would be enough data to make a significant measurement or not. But yeah, so indeed, you have to take care of this. And you could, for example, also try doing simulation with new physics models included. And then see maybe this matches your data better, for example.
Okay, so very good. So one of my other questions was actually maybe precisely on that, because I guess one of the reasons that you have to do this correction afterwards is because you don't want to rerun the simulations, right?
Don't want to, sorry?
You don't want to rerun your simulations. You have to correct for them afterwards.
Yeah, so this is part of it, and also because the some of what comes out of the simulation is also, so you would have to fix the simulation first. So you have to go really into the code that's used to the simulation, maybe in the PTA and the QCD simulation or so, and then see, oh, where is it going wrong, and fix that. I think this takes a lot of time, but I would say that the time spent by all the PhD students combined with correcting the simulation, you could have probably fixed it already. Yeah,
so that was indeed what I was going after.
Yes.
If for the future, maybe there would not be a better alternative.
Yes,
here.
I do agree with that, yeah.
Okay.
Because also I say it's an error-prone process, and this is, I mean, when you do these analysis, you do run into these things. So you have to be careful not to double correct something, or maybe inside your trigger selection, there's already a PID selection done, so then you have to make sure not to also then correct the PID selection separately, to do it twice. So yeah, it's you have to be careful.
Do you have time for another quick question? Okay, so my other question would be about, no, I have to be quick. page 91. Right. So here you are looking at, well, in order to measure R lambda, you now already did some pre-measurements of other ratios. And you also say, okay, what we see, it's a bit Uli's question as well. What we see is you get something that is below 1, which is what you're expecting. And then you say, okay, this could be because of the electron yield, that you have wrong efficiencies there. And you also say what you plan to do maybe in the future with more data. Can you elaborate a little bit on that?
Yes. So indeed, as you can see now in this plot, the uncertainties are very large. So we don't have so much data, which, if you want to further investigate it, makes it maybe difficult because you, for example, want to check these values in different kinematic regions or so, which means you have to split your data sample further.
And here, kinematic regions was not so clear to me. It's q squared.
For example, q squared, or just the lambda b momentum, or the momentum maybe of the electrons, maybe something is going wrong. You can check many different variables. Because if we think we expect it to be done with the electrons, maybe something is wrong with the electrons. Maybe you would start by studying the q squared, the momentum and the energy of the electrons, and see if maybe, for example, for low momentum, something in the measurement is going wrong, or something in the simulation is not correct, for example. So these things you could check. Yeah, and maybe another thing you can do is check it at one thing that, well, maybe you can do it now already, but I didn't have the time to do it, is to check it at different stages of your selection. Because we apply multiple selections, maybe a mass selection, or some also the PDT selection, so the machine learning classifier. Maybe you can check it before and after that and see if it skews your ratios. So this is something you could do now already, but if you would zoom into these different regions, I think you do need more data. Maybe you can, for the JPSI mode, maybe you can get away with 2 bins or so by splitting the data set in half again. But otherwise, your uncertainties grow so large, I think it's not providing much meaningful information anymore.
Yeah, so one of the questions I had, if you would now do that, if you would have to run 3 data or any data you have, and you find out basically what is wrong, could you then go back to your run 1 and run 2 data and correct for that as well, or do we have to throw that out?
No, you could in principle reuse the data. If you're measuring with a different detector, so you have to be a bit careful. The data is not exactly the same, but if you find something that's going wrong in, for example, reconstruction software or so, then of course you can also fix this on the run 1 and run 2 data. Although it also at some point becomes the question of how large the data set in run 3 becomes to run 2 and run 1. Because if it really grows a lot to what are the expected numbers, then maybe the run 2 and run 1 will not add so much more to this. And maybe we better to only do it. Because it also, looking at the older data comes with a lot of problems by itself of like, okay, you have to use different software for some things, and you have to make sure that corrections are applied correctly.
Okay, thank you. I give the word back.
Thank you. The opposition will be continued by Dr. Jaco de Vries from Maastricht University.
Thank you. Dear candidate, beste Shane. I also want to congratulate you on the nice summary of all the physics. It was very clear to read, but specifically the part about the time alignment of the SciFi detector. It's being used as a manual now for the next generation of students at CERN, so I think that it's commendable how thoroughly you've written it down. So that's very nice to see. Now, I can ask you a few questions about the physics. And my first question is actually about proposition number 6.
Performing independent analysis measuring the same quantity is a powerful cross-check of the analysis methods and results, and allows for finding and correcting mistakes.
Thank you, Sylvia. So about this, I tried to find in your thesis where there was something that you learned from the other group that performed the analysis independently, and I couldn't find it. So could you maybe tell us something about what things you uncovered because there was a separate independent group working on it?
Dear esteemed opponent, thank you very much for your kind words and your question. Yes, so indeed, it's not explicitly mentioned, but the whole analysis on the branching fraction of the lambda b to JPSI lambda was also being done by a different group. And we were focusing more on the downstream reconstructed tracks, and they were focusing on the long tracks. So these are 2 track categories. So basically, with the downstream, we don't have the information from the fellow, from the vertex detector. And one thing we saw was when we were measuring, okay, we do the whole analysis, and then in the end, we saw that some ratio of yields do not agree with each other. So if you correct for all your efficiencies and if you correct for everything, you should in principle measure the same quantity because you're measuring the same thing, but they were not in agreement. So something was going on. So we started looking, okay, what is going on? And actually one of the things that we found through this was, which is described in chapter 5, from page, well, let's say on page 61. We started looking at some point, okay, how do our more low-level detector quantities look like, and does everything agree there? So this distribution here showed the distribution of phi of the, in this case, the k short and the lambda in bins of the eta, so really of the kinematic regions of the track, so to say. And we saw there was a little dip going on. If you see the bottom right plot, you see the strongest. There seems to be some kind of mismatch between the data, signal data, weighted data, and the Monte Carlo. So something there was going on, and they did not see this in the long tracks. So this is a hint, okay, something is different between our work and their work. And then we started investigating this and see, okay, what's going on? And actually we realized that one of these sensors in the TT, so the tracker that is used to measure downstream tracks, it was broken at some point during, I think, 2017 or so. This one sensor in the detector broke. And this, it was a bit hard to find this written down, but somewhere it was written down. And then we started realizing, oh, okay, if we then look at the data in 2016, for example, to 2016 it looks okay still, but in 2018 it doesn't look okay anymore. So something is going on, and this is what you show in the plot here on the page. And then if we decide, okay, then we cut out this sensor, we veto this sensor region, the disagreement disappeared, and the data agreed again. So this is kind of how you can find these kind of things. I think otherwise, if we wouldn't have measured with these two separate groups, we would have never encountered this issue, because probably we would have been, okay, the measurement looks good, so we continue onwards with it. Or probably you would have opted to only measure it with long tracks, for example, because you have a higher resolution, because you have the vertex information. So you would never have encountered this. So these are the kind of things you find, and I think, I think it's good to cross-check, but it also takes a lot of time, and it points out a lot of issues you have, which is good for the quality of your research, of course.
So what would have happened? I mean, this is a beautiful study, of course. I completely agree. But what would have happened if you didn't encounter this? Would it be something that would turn into a Monte Carlo data difference, and there would be a small systematic added to this? In the end, was it essential, maybe?
That whole thesis is essential. Indeed, it would have been some difference in data Monte Carlo, and therefore wrongly estimating your efficiencies. So your ratio would have shifted indeed by a bit. This is what we saw. In the end, you combine the measurements, so probably you would have given it some kind of systematic uncertainty, because the goal is in the end to combine the results of the long tracks and the downstream tracks to give a single measurement, like a simultaneous fit. But it probably would have been there, and you could have assigned the systematic uncertainty maybe, 2% or so, and be like, okay, it's a conservative estimate. But then you still, you lost information because you didn't know what is going on. And actually, it's something that's wrong inside the detector. So I think this is, I think it's better to do know it than not know it, I would say.
So how many things are there that we don't know yet about?
Yeah, that's a good question. It's the unknown unknowns, I guess. There's probably many of them. In general, the measurements seem to be going, and things seem to be in agreement. So we're doing something right, I would say. Not everything is wrong, but you do these kind of things you can notice like this.
Yeah. So about that taking a lot of time, I know there was a lot of struggle to get the analysis aligned as well. So maybe that's one of the main reasons that it took such a long time to get something published about this, or something out, I should say. So is it worth all of that time?
Excellent question.
Maybe the question is, should we do this always in LHCb or not?
I think for the quality of the analysis, it's probably good to do it, because you do find these differences. I would say with the limited people power we have, maybe it's not worth it, because you can do many more things with the time with other people have. But in principle, I would say yes. We learned so many things from doing this together. And also, you spot many mistakes that maybe otherwise you wouldn't have noticed. I do say that it would probably be good to do it systematically from the beginning, because at some point we found out other people were working on this. So, but then you can maybe make sure to align everything from the beginning, because they were, for example, using a different stripping line, to come back to stripping, which then had slightly different pre-selections to what we were doing. So then we have to make sure that afterwards we align everything, and then maybe a PID selection is slightly different. So it's very easy for these things to sneak in if you don't actually control it from the beginning.
Okay, that's very valuable. Thank you.
Yeah, I think it is.
Yeah. So I have another question. And it's on page 42. Where you talk about the particle identification. And on page 43, I see that for the muons, in figure 4.11, you have a relatively fine binning. So you get, in bins of kinematics, you get the efficiency dependency very, very precisely. But in the plot below it, you do this for the electrons, and here it's much less fine. What's the reason for this?
Yes, indeed. So it's because of multiple reasons. So one of the reasons is muons are easier to reconstruct, at least in LHCb. They're easier to measure, so we have also a larger data set for it. And we calculate the efficiencies in a kind of different way for the muons and for the electrons. So for the muons, we use something that's called PID calip, which is a bit of a technical term. But this is some predefined software in LHCb that can give us these kind of efficiency maps for your specific selections, which then uses these large data samples of these J-psi decays to go into muons. And what you do is you have a very high selection on one of your particle identification on one of the muons, then use the other one to measure the efficiency. But for the electrons, we have to do it a bit of a different way, because they're I think that this data set is not available for electrons also, and you might get a biased result because I think the PID calip uses S-weighting, and this is maybe not good if you have a very large resolution on your measurement. So for electrons, we use this, what we call fit and count, although I know that my current opponent has a different name for it that he prefers, bin and fit, but okay. I stuck with the original LHCb naming for it in my thesis. And in this case, what we do is we do basically kind of the same, but we do this by fitting the different data samples. So you perform a selection on the PID, and so first you have your data without the selection, and you have your data with the selection, and you both individually do a invariant mass fit on these decays. And then from this, you can get these numbers that are shown in equation 4.9, where we have the number of passing the selection and the number of failing. And then your efficiency is the ratio between these two. So we fit these decays, we get these numbers, and then we make this mapping. And so because we have to do this fitting in all of these bins, you have to do it individually for each of these bins in kinematic region. If you start to bin very finely, it becomes very difficult to do this invariant mass fit, because there's not enough events anymore to fit. So this is where this difference in resolution comes from, or in the binning maps, basically. Because we have to do this fit, we make them a bit bigger.
Yeah, that's fair enough. Though I would argue that we know that the efficiency of the electron PID versus momentum is quite dependent on the momentum at low momentum. And here you don't have the bin granularity to be sensitive to that. So I'm a bit worried that just because you can't fit these bins, or it's a lot of work to babysit all of these bins, that you don't capture the behavior well enough. So I was looking for a systematic error or a systematic uncertainty because of this effect, but I couldn't really find it.
Yes.
So do you estimate this, or do you compare with PID calip, or is this something that you do?
So this would still be something that has to be done, indeed. So this comes back to my proposition number 9, where we have to decide with the time that you have what to do. And there's indeed many things that we have to do for these analyses, and calculating systematic uncertainties is a large part of it, indeed. But yeah, you could, for example, do the same process, maybe using S-weighting, for example, as a way to compare it, or then use different binning, maybe change the binning scheme and see if you can capture this dependence, and maybe by measuring these different ratios, you can potentially assign a systematic uncertainty. But indeed, it is in the current thesis this here. It's not yet performed, but it is something that should be done before the analysis is going into final publication, I would say, because it is something that could have an effect on your ratio, especially in these ratios where it is so sensitive to know your electrons and your muons. I mean, if you're measuring the double ratio, it's already a bit less, but if there's a kinematic dependence, this could also come then back again in the q-squared, what was mentioned before, where you could have a different q-squared dependence because your electron measurement is wrong. So,
Thank you.
Lex Greeven, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and of your defense. I request that you and your company await the result of our deliberations and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. All your time, cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you won the battle once you've grown. South side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Lex Greeven. The degree committee here present has assessed the quality of your thesis and of your defense. In view of its positive verdict and taking into account your previous qualification, the degree committee has decided to grant you the degree of doctor. Professor Merck is authorized to confer upon you this academic distinction in accordance with Dutch university custom. And so I invite your supervisor to now take the floor.
Please all rise.
Belooft u dat u altijd volgens de beginselen van de wetenschappelijke integriteit te werk zult gaan, eerlijk en zorgvuldig, transparant, onafhankelijk en verantwoordelijk?
Dat beloof ik.
Krachtens de bevoegdheid ons door de wet toegekend, volgens het besluit van de commissie hier tegenwoordig, verklaar ik hierbij u, Lex Marinus Greeven, tot dokter te bevorderen en u alle rechten te verlenen die daaraan volgens de wet en gewoonte zijn verbonden. Ten bewijze hiervan overhandig ik u zo meteen de bul door rector, secretaris en overgeleden van de promotiecommissie ondertekend en met het grootzegel van de universiteit bevestigd. Wel edel, zeer geleerde Lex Greeven, van harte proficia met het succesvol verdedigen van haar proefschrift, verdutsen van het chique kwark, zal ik het maar noemen. Chevraaien lopen me over de rug. En op dit benkelijke moment u, Lex Greeven, in het Maastricht te mogen verwelkomen als nieuwe dokter in de wetenschap. Ook een dikke proficia aan familie en vrienden aanwezig. Well, after having started the laudatio in the only important language of the world, of the center of the world, obviously Maastricht, I should perhaps use some other secondary language as well. Lex, let me just unfold this. I believe we first met after an evening talk in Maastricht. Was it of the Aperture Study Club, where you were co-organizer? And I do remember a very nice atmosphere, an enthusiastic Lex, and snacks and drinks after the talk. You do know how to lure a local to come and speak to such events. Very good. Afterwards, you came to NICEF for your bachelor thesis project. You must have wanted it very, very much, because I remember you were living in Amsterdam, somewhere in some basement, basically a closet, but paid a fortune for it, for the rent. And you were one of the pioneers of students from MSP to come to the research of particle physics at NICEF with a bachelor project. And the topic of your research was flavor mixing and CP violation with BS to DSPI and BS to DSK. Now, many here know that this is still my personal favorite topic of research, because one can really see the CP violating quantum mechanics, happening in front of your eyes on a centimeter scale. It's really a fantastic measurement. And you did it very well, without any prior experience in the field. You worked out the full theory formalism, I remember, of this BDK probabilities, and that's something that I personally only tried to do 2 postdocs later in my career and halfway failed, I believe. Subsequently, you fitted this data with, at the time, I remember, a novel Python software package. Now, I remember how smart and hardworking you guys are. You know, this shows that we cannot do this anymore, but young people, they have an excellent education and can do these fantastic studies. To put these things actually in contrast with my own digital clumsiness, I once, for fun, I should say, I added in emails the name Lex Greeven, and subsequently never managed to get that out again. With the consequence that I have been sending mails to everyone in the collaboration with that add-on to your name. So my apologies, Lex. It is really just my clumsiness and nothing else. Preparing this speech, I read again your self-reflection of the BTR that you wrote, where you said, although MSP courses provide a good basis, a small learning curve is still present. Also, the increase in difficulty was substantial. So being a teacher now, and this was probably an understatement, I guess, but being a teacher now at MSP, I can appreciate that. And it shows, Lex, that you are a shining example for MSP students with your motivation, your skills, endurance. You just did it, and your work was really of excellent quality. And in fact, I just realized by yesterday, Chris mentioned to me, you are probably the first MSP student who made it into a PhD in physics. So in Maastricht, our town, I think it's amazing. To prevent spending another fortune living in Amsterdam after your bachelor thesis, you looked for a master in other places and found a very good education in Bonn, where your research brought you in contact with rare decays and the Bell II experiment. Now, seeing the difference between a hadron machine and a lepton collider, in particular about the coherent BB bar production, is extremely valuable. It has given you an excellent preparation later on for your PhD, I believe. Indeed, you had a flying start in your PhD work. Your contributions have been many, resulting in a beautiful thesis of baryonic decays and the SciFi work that you presented here to us. And as you wrote in the acknowledgement section, the SciFi work started as a side project, but became your favorite project in the end. So you successfully managed to combine a data analysis project and a hardware project. The hardware project sometimes we call service work, but I think it's a wrong name. It's a beautiful technical research project, which is both satisfying, apparently, for the student and important for the collaboration. I advocate that all students should do such a combination of technology and physics. Lex, we're really grateful for your excellent contributions to LSCB. Let me also for one moment address your role as enthusiastic and central member of the BFIS group. You're always available for organizing professional and fun happenings. And thanks to persons like you, the atmosphere in our group has always been great. And it was a certainly absolute pleasure for me to witness that. Many thanks for that, Lex. Keep that approach. In the future, it will bring you much pleasure. For the final year at NICAF, coming to the end, you were sitting in the office directly opposite to mine, in the corridor. I hereby apologize for all the noises you and your fellow PhD Jordi must have endured coming out of my office. My frequent "God, meneer" must have echoed through the corridor many, many times. Apparently, some people have occasionally mixed you up with Jordi, in fact. I will not mention specific persons. In fact, one of them was supposed to bring 3 copies of your thesis yesterday. So this is the thesis he brought. The thesis of Jordi. But I personally, I cannot understand that at all. You know, if you guys would, you speak different languages, I just don't get it. It actually reminds me of this old joke that I learned at primary, at kindergarten, in fact, about this silly joke about a Belgian farmer who had trouble to tell 2 of his famous horses apart. And he studied it, and he tried and figured it out, until at one day he discovered that actually the black horse was a centimeter taller than the white horse. And that did it. To me, it's a similar comparison with Lex and Jordi. So Lex, your contributions, work attitude, and personality were a jewel for the group. It's always a bit sad when students move on, but I'm sure you're moving towards an excellent future career, albeit you're apparently not allowed to talk about it. That's a pity. Finally, Lex, nog eens een dikke proficiat. Ik wens je het allerbeste in de carrière en persoonlijk leven. En ik weet het zeker, voorzien is. Congrats.
Thank you.
Dear Dr. Greeven, also on behalf of Maastricht University, I congratulate you with the degree you have acquired. These may look like small little booklets, but they take an awful lot of grit and determination and inspiration to will into existence. And, well, without you, this would not have existed, and the world would have been that little bit poorer. So, very well done. I told you it would be festive. I will close the ceremony in a second. Then we will head off to the big staircase to take a little picture, and then you can all, dear audience, move over to the after, where we'll be able to reassemble very soon for a celebratory drink and a toast. I hereby conclude this academic ceremony. Don't forget.